Hello, Professor. My name is Rashid Osho, and together with my colleague Olikawa Fashion, we shall be presenting our project report on assessing the viability of hydrogen production and storage system in Nunavut using wind and solar hybrid system, and we are focusing on Rankine Inlet. Rankine Inlet, just like the other 24 other communities in Nunavut, is heavily dependent on diesel power, so that poses a lot of environmental and economic impact on the community. And so our research is looking at the renewable energy, particularly wind and solar, to produce energy, to produce electricity for them, and by extension we're looking at using wind and solar to produce hydrogen so that we can solve this problem. This project is divided into two scenario cases. Scenario one, where you're looking at analyzing the wind and solar energy techno-economic aspect for replacement of the diesel system. Scenario two will be looking at evaluating the use of wind and solar to produce electricity and also to generate hydrogen. The objective of scenario A is to conduct a techno-economic analysis of wind and solar energy and focus on replacing the diesel system with the renewable energy. Objective of scenario B is to perform a techno-economic evaluation of the wind and solar energy as well, and also to look at a way to produce energy and use that electricity to produce hydrogen in Nunavut, in Rankine Inlet. Rankine Inlet is located in the Kure Peninsula in Nunavut. It's the second largest community, just after the Iqaluit, which is the capital. It has a population of about 3,000 people, and it occupies a square meter area of about 20 square meter area. The existing diesel system in Nunavut and the challenges. A look at the table shows us that the diesel generator in Rankine Inlet was established in 1973. What that means is that it's old, with attendant repair and maintenance, which is making the cost of electricity to be quite high. As seen from the table, the cost of electricity in Rankine Inlet is 49 cents per kilowatt hour, which is higher than the national average of 0.192 kilowatt hour, and that calls for immediate attention. Methodology. As I said earlier, we have divided this study into two scenarios. Scenario one is looking at the techno-economic assessment of wind and solar energy to replace the existing diesel system. Scenario two is looking at evaluating utilizing wind and solar energy for both electrical energy generation and hydrogen production. Case study one, which is evaluating the wind and solar power energy to replace the existing diesel electricity. The Rankine Inlet load is about 17 million kilowatt hour per year, and that comes to about 2.3 megawatts, and with a reserve margin of 15%, it comes to a daily load requirement of about 55,000 kilowatt hour per day. So what that means is that the proposed renewable energy solution must be able to meet this need at a cost that is competitive. The load estimation, as seen from the table, we have the turbine, we have the PV panel, we have the converter, we have the battery. These are the components for the system architecture as seen in the schematics. Looking at the solar energy generation, the equation 2 shows the electrical power that can be generated from solar using that PV panel. Next, we look at our results and discussion. As seen from table 3, the MPC is about $104 million. the levelized cost of energy is 0.3986, while the operating cost is about $2.6 million. As seen from the graph, the graph gives us a summary of the system component, where we have the turbine, we have the battery, and other components, and we can see the result as shown on the graph. Next is the cash flow. As seen, we can see that on the graph, the capital cost is a bit high, followed by the operating cost, and finally we have the salvage, which is coming from the turbine and the battery. Still continuing the result and discussion, the generation of power with the proposed system is 36,000 kilowatt hour, majorly coming from turbine. Turbine is giving us 99%, while the solar PV is giving us about 1%. And next we see the graph which compares production with consumption and excess. Production stands about 20 megawatts of megawatt hour, while the consumption stands at 20, and then we have excess of about 16 megawatt hour. The excess can be used for other application. We can even sell it to the grid and make some money for the community. Finally, under case study 1, we're looking at the economic analysis and comparison with the diesel system. From the table, we can see that with this proposed system, we will be saving. Of course, first we're seeing that we're generating even over 100% of the required load, which means that the system, can actually replace the existing system in Rankan. We can also see that LCOA is 0.39, which is less than the cost of the electricity. Electricity is sold at 49, while the LCOA is 39. That's very good. It means that the project is investment worthy. We can also see that the diesel system is consuming about 4.6 million liters of diesel every year, which comes to about $5.6 million that will be saved with the use of this proposed renewable solution. And finally, we have the GHG emission coming to about 14,800 tons of CO2 equivalent with the use of the diesel system. With the renewable energy solution that we're proposing, that amount of GHG will be saved, and if we apply the rate of emission, which is about $50 per ton of equivalent of CO2, we would have an annual saving of about 740,000 Canadian dollar every year. That comes to a lot of savings. So it means that this system that we're proposing is economically viable, and the impact on the environment is also quite minimal.
Hi everyone, my name is Oluwaka Odufashami. So I'm here to expand more on case study 1 by incorporating the hydrogen production into the entire systems. So the annual cumulative electrical load will not the annual electrical load in Rankan Inlet is 17,625 megawatt hour per year, which is running to a daily average of 48,287 kilowatt hour per day. This simulation, we have an additional energy load of 1,280 kilowatt hour per day, which is required for the compression and intercooling process of hydrogen at a rate of 6 kilowatt per kilogram to store about 205 kilogram per day. Consequently, the total energy demand will not amount to 49,417.70 kilowatt hour per day. By factoring the multiplier factor of 1.34 with the adjustment, the total load will now result to 66,440 kilowatt hour per day, picking out 16,631 kilowatt. These are the generation sources in the proposed system will cater for the more electrical load and the power that will be required to generate more hydrogen through the electrolyzers. As I mentioned earlier on, these are the parameters we consider. According to Statistics Canada, the total number of registered vehicles as of 2019 in Nunavut is about 7,019 vehicles. So that means that by using the mathematical modeling, since we know the total populations to be 36,858, with Ranka Inlet having about 2,175, we can deduce that the total numbers of cars using in Ranka Inlet to be 573 cars. So that means that by considering 2.5 kilograms per vehicles per week, by doing these calculations, we can conclude that that Ranka Inlet will be consuming about 205 kilograms of hydrogen per day if we are to use fuel cells electric vehicles in Ranka Inlet. The system architecture is set up. The total equipment the whole equipment we are using for these simulations are listed in table 6. As we can see, PV dedicated converter storage, battery storage. In this case, we are considering a generic battery, 4 hours, 1 megawatt lithium-ion battery. We are having a size of 12 strings, a system converter of CAT BDP 250s, electrolyzer of about 10,455 kilowatts, and the dispatching strategy we are using here is Oman load following. Figure 8 shows the entire system architectures of the whole process, of the whole system. The mathematical modeling considered for this research here is listed in equation 3. Here shows the probability energy density function for the wind turbines, while equation 4 is showing us about the annual energy productions of the wind turbine during a specific period. Continue. The wind power required to produce the wind energy required to produce hydrogens. The equation is listed in equation 5, and the annual energy output for the PV systems here is listed in equation 6. The economic analysis, the net present cost here is listed in equation 7. The levelized cost of energy is captured in equation 8, and equation 9 illustrates the equation for the levelized cost of hydrogen. Electrolyzers. Then equation 6 and 7 is showing us the equation for the electrolyzers. Your cash flow analysis. The breakdowns of each component of cash flow is listed below. As we can see, card PDs 250. Then the Enercon E115, the generic lithium-ion battery. The electrolyzer used for this simulation is listed here. The hydrogen tank is also listed there, which is at the cost of 20,500 annually across the 25 years period, and the electrolyzer is at the cost of 375,000 a year. The extruder various string PS120 used for the simulation is also listed here as well. Likewise, the second turbine used Vesta V8 is also listed here. As I mentioned earlier on, all the systems used here are listed below. Thank you. Figure 9 shows the cash flow as the total cost incurred happen at the first year, which is year 0, and the system and the whole investment will start making profit at the last year of the project, which is year 25. This means that there is possibility that if there's an investment on this project, it will surely make profit at the end of the day. System financial summary, case study 2. Table 6 shows the system cost summary with total net cost present at $69 million. The levelized cost is about $2.258, and the levelized cost of hydrogen is about 69.9, which is way far more than the industrial average, which over between $10 to $15 per hour. The operating cost is about $1,512,421. But as we can see here, Though the cost of hydrogen is quite high, but if you are to compare with the levelized cost of the energy, which is like half of what is priced presently at Nunavut, this shows that the savings made from the energy can be used to augment whatever the cost that may be incurred in hydrogen, which made this a more cost-effective solutions. The total power production is very peak at 69 million, while the total power consumption is about 44%, which leaves us to have an excess of about 60%. This shows that this excess can also be redirected to some other use, like selling it as a raw power to the neighboring country, or directing it to produce more hydrogen, which can also be useful for the community. Table 7 shows the solar wind hybrid system with hydrogen productions versus existing diesel. Currently, the existing diesel is producing 17,625,000 annually, as compared to our proposed solutions, which have the capacity of producing 44,537,838 kilowatt hour. This shows that this new system, these proposed solutions, will produce more energy, and that shows that the total energy produced by our proposed hybrid system is way more than what is currently being produced at Ranka Inlet. The levelized cost of energy as well, we are producing the new solution is producing at the rate of $0.258, as compared to what is using at the Nunavut at the moment, which is about half the price. Now the levelized cost of hydrogen. There's no hydrogen production at the Nunavut at the moment, but as compared to the proposed solution that we are considering, we have to produce hydrogen at the rate of $69.6. This seems to be much more higher. But if you have to contrast it with levelized cost of energy, which is about half of what is currently pricing energy at Ranka Inlet, the savings made from this are used to augment whatever the cost of energy being produced. Then there's also savings. There's no fuel utilization. The economic implication will make enough savings from the cost of fuel. We make enough savings also from the GHG emissions. We also have, if you have to sell the hydrogen at the rate of $12.5, we make about $935,000, which makes this particular solution an investment worthy. If you are to table 8, compare the three scenarios together: the existing diesel system, the scenario case 1 and scenario case 2. As you can see, out of these three systems, it is only the existing diesel that is producing a very low amount of power annually, which means that the remaining case scenario 1 and 2 produce much more annual energy as compared to the existing solution. So either of the two case study can replace the existing system being used at Ranka Inlet at the moment. In terms of the total energy production, these two case scenario produce way more energy as compared to what is being used at Nunavut. And also in terms of the levelized cost of energy, the case study 2 and 3 tends to be much more lower as compared to what is currently being paid at Ranka Inlet. Then, as the levelized cost of hydrogen is only levelized in case scenario 2 that's actually producing hydrogen, but it's producing at a rate of $69.90. Then, in terms of the GHG emissions for utilizations, none of these two case scenarios is actually producing anything. It's actually consuming anything as compared to this. So this means that two case scenarios are much more environmental friendly as compared to what is being considered the Nunavut at present. Environmental and sustainability. Using the renewable solutions such as these two proposed case studies has significant environmental benefits, such as reducing GHG emissions, mitigating climate change, improving the air quality, preserving the biodiversity, protecting the ocean health, promoting sustainability, perceived barrier to renewable energy projects in Nigeria, perceived high capital increase, the negative impact of renewable energies on the land and the other area, the knowledge gap and the lack of sufficient information, the lack of appropriate management strategies, shortage of local skills, regulatory framework. Conclusion: Ranka Inlet possesses abundant wind resources, but is limited in solar energy. Wind power can produce sufficient energies. Then a meticulous financial comparison between the current business and the two renewable scenarios demonstrate that the shift to renewable energy is poised to eliminate the entire annual expenditure on diesel, resulting in substantial economic savings. Thank you.